So one of the things we saw yesterday, we arrived at this nice conclusion, which is that if you give me the CFT data, which means the set of all these power law behavior critical exponents delta, and also the set of all 3-point functions, which are parameterized by this number Cij, the claim is that once you give me this set of numbers, I can then take two operators, replace them by an effective third operator, or a sum of them, and obtain any correlation function. For example, suppose I take a 4-point function of operators that have the same dimension for simplicity. Then we know that there is some power law dependence that I strip out. That's some simple dependence that makes sure my object transforms appropriately. Whatever multiplies it now must be a function of the two cross ratios, which is invariant under conformal transformations. And it can be written as a sum of a product of structure constants of 1, 2 fusing in the operator k, and then k decaying into operator 3, 4, which is the picture drawn here. And then there is this function fk, which was totally fixed by conformal symmetry, as we saw yesterday. So it's kinematics. It's like spherical harmonics or plane waves. Plane waves are what we do when we have translation invariance. Conformal blocks are what we use when we have conformal symmetry. So the fk is an object that if you give me a primary of dimension delta and spin L, and I want to sum over all operators, you just say I sum over the primary of dimension delta and spin L, and the descendants are automatically captured by the conformal block. And it's a function we compute once. And I told you how we would compute. Okay, so I explained yesterday how one way of computing by brute force. You might say it doesn't look like the most efficient way. It was the way that people computed it the first time. Now we know many more efficient ways of computing it, but that was actually the way Dolan and Osborne first started computing these conformal blocks in higher dimensions. Okay, and these conformal blocks the only ingredient I'm putting here in the blackboard that I didn't discuss yesterday was the statement that in general we also have spin L. So in general, if you have two scalars, and you take scalar O at x1, O prime at x2, and you fuse them, and you get a third operator, you can ask, does the primary that I get, does it need to be a scalar, or can it be a tensor? Right? So if I have O at 0, O at x, and I want to make some object with indices, right? The only tensor that I have to construct is, the only thing I have to construct the tensor with is x mu. And therefore, the only thing I can do is construct symmetric traceless tensors, because I need to contract with x mu, and if it's not symmetric, I can just symmetrize because I'm multiplying by many powers of x mu. Anyway, it's a consequence of group theory that if I take two scalars, I can form only symmetric traceless tensors. So in the OPE of two scalars, OO, we can have a scalar, or we can have symmetric traceless tensors, which are objects which have mu1 up to mu_s, and they are totally symmetric and traceless in these indices. So for example, a spin 2 object, right? Okay? So they are parametrized, or mu1 up to mu_l. So they are parametrized by this integer L, which can be 0, then it's a scalar, or can be 2, and so on. Right? And we have to sum over this spin L as well. And if you check the derivation, and if you ask, what would I need to know in order to construct this function? What's the modification that I would need to do? Well, when we did OP of O with O, I replaced by a sum taking into account only the primaries. So I will need to know what's the OPE to produce a spin L object. So the only thing you know to change a little bit the derivation we saw yesterday and capture this function here, I would have to tell you that O with an operator of spin L, mu1 up to mu_l, is also fixed by symmetry. Okay? And this, you can easily see that if this is true, then I can just go to the derivation, add a bunch of indices for spin L, an extra sum over L, and everything goes through, obviously. Because this is like just say that this is a collective new index K. So if this is known, everything would go through. Okay? I don't want to explain why this is known by symmetry and how to constrain it. It's something technical that it's easy to study, so I'd rather tell you about more complicated things. Okay, so what is this F? We saw how to construct it as an expansion, a power expansion, and then I told you have to work very hard and compute 1 million terms, see some pattern, resum it. And there is the result, for example. In 4 dimensions, that's the result you get. I see, it's not super complicated. It's also not super simple. This F is a bunch of hypergeometric functions. Okay? But as I said, it's like Bessel functions. You compute it once and it's done. It's a function that depends on the delta of the exchanged operator in this case. If all operators have the same dimension, actually the dimension of the external guys doesn't show up. Okay? Which is not totally obvious, but if you check the first coefficient that we computed yesterday of the expansion of the conformal block, you will see that it depends on delta 1 minus delta 2. So if they are equal, it just disappears. But it does depend on delta k, which is the exchange of the middle operator, the dimension of the operator being exchanged, and on the spin of the exchanged operator, and it takes this form. Okay. How did we think? Again, we said that we fused, so there was these 2 pictures which are absolutely equivalent. Either we think in RD, and we say that I put a sphere around these operators. I have some state here now on the sphere, some functional, and it evolves, and gets annihilated by these 2 operators, right? And the evolution will be characterized by the quantum numbers of this evolution, which are the dilatation and the spin as I rotate this sphere. And that's why I sum over dilatations and spin. Okay? Okay, so because we take these 2 operators, replace them by a 3rd operator. The other way of thinking, which is equivalent, is by saying, well, the operator I put at the origin, say, I think as generating some ket. Then this state evolves, this ket evolves, this ket 1 evolves, and it gets hit by operator 2, and it produces some state psi, right, some new state psi. And this new state psi, because it's in the Hilbert space, can be written as a linear combination of primaries and descendants, like this, right? And I decompose it. And now that it's decomposed, I can evolve it back to the past. Why? Because what is evolution back to the past? Each of these guys I just multiply by a phase or by an exponential of the corresponding quantum number, e to the minus dimension times tau. So nothing singular happens, and I just evolve it back to back in time. And I start here, I evolve it back in time, and I get a new operator at the origin, which is a linear combination of many operators. And someone asked, and let me repeat, that why this would not work, why would this not obviously work if I have a massive quantum field theory? Because the big difference is that in a massive quantum field theory, I would also generate here some state in my Hilbert space, but the evolution backwards in time, it's not just exponential of some constant Hamiltonian times tau. Now it depends really on the scale, and when evolving back in time, I could eventually find some new singularities here, a cut appearing, or something that would not forbid me to go all the way to 0. You might say, does it happen in realistic scenarios? Do we have some strongly coupled quantum field theory where such crazy things happen? And the answer is we don't have any solution of a strongly coupled quantum field theory to test these ideas. So yeah, it's up to you to solve them and then tell me what happens. But in a CFT, we proved that it cannot be. And one way of understanding what we are doing in this picture of the cylinder is very simple. We take our state 1, we act with state 2, and we generate a psi. From the other side, we start with a bra 4, we act on 3, and we get some state psi prime. And what do we do in the middle? We insert a resolution of the identity, saying I sum over all states, so I resolve my identity. But then when I plug this identity here, this is what I get. I sum identity, 4 gets hit by 3, produces some state, I overlap it with k, and then k goes to 2, goes to 1. And these are these 3-point functions. This is what gives me this C3, 4k, and this will be what gives me C1, k4. And of course, this is schematic, and in formulas, it is very explicit formulas. It's this with these very precise conformal blocks. Questions? Yes?
I'm not too sure about this, but we have 2 operators with spin 0, and they're fusing in to give you something which is non-zero spin.
Yes.
So basically, how does this work? You can't It's not like you can add angular momentum and get something.
Oh, the question is, how come spin is not conserved? How can I produce spin if I start with scalars? And the answer is that they are not at the same point in space-time, right? So if you have 2 points, you can form something that spins. It's just like the Earth and the Moon. They are both scalars, and yet the system has angular momentum, right? Similarly, we have operator O. So let's see the quantum number. So if you have O at minus x times O at x, what I'm saying is that I can easily generate an operator O mu1 mu L, and I contract here with x mu1 x mu L. In the OPE, there's no problem in generating a symmetric tensor object, at 0. Right? With x's, I have enough. I mean, you see, this has the right indices structure, so it just disproves what you are saying. But the intuition is that if I have 2 operators, and if by spreading them, see, now I'm giving it some orientation. I start with a scalar, which has no orientation, just a point. I take 2 scalars and I separate them. Now I have an orientation. I generate it. So it's just the fact that by separating points, the intuition is like you have a rod and you are stretching it and giving it spin. Okay. So, more questions? Okay. So I'd like to tell you some cool recent developments about this conformal block expansion that people have done over the past year or two, and then tell you a little bit how this story, some new things about this kind of stuff that we could do, and then go to n equals 4. Yeah, it's going to be a morning. Yeah, I might go a little bit over time today. So I want to point out the following. Suppose I have 4 points here. Okay? And what we are deciding to do is the following. We are saying, I can put a sphere around these points and expand operators, say, around this point here. And then study what flows from this channel to this channel. But I could have chosen a different channel. I could have chosen this channel, this circle here, and say we're expanding around here and study what flows from these 2 operators to these 2. Right? And the 2 options better give the same result. In terms of, right? So yeah. In other words, in more mathematical terms, we want to have associativity of the operator product expansion algebra. So it's an algebra that tells me that if I take 2 operators, I get a 3rd operator. But I can fuse O1, O2 or O2, O3. I can choose to fuse in different orders. And I should get associativity of this algebra. Okay? And this immediately can be translated into an equation. This implies that a CFT must be such that the sum over K of C1, 2K, CK, 3, 4, times the conformal block, which is drawn as this picture here, right? No one complained here. I forgot to define. And U and V are the cross ratios we defined in one of the lectures. Okay? So this expansion here, where I expand 1, 2 going into 3, 4, right? Should be equal to the expansion where I expand in some other channel. Okay? Where I expand in 1, 3, 2, 4, say. I actually prefer like this. Sorry. Okay? Which stands for the equation sum over K C 1 4k, C 2 3k, and now we will have the conformal block. But if you remember, this amounts to changing the points. This I will put here 1 minus z, 1 minus z bar, because this amounts to changing u and v, which is what this transformation does. If you remember, I define v as being u where I flip 2 and 4. Okay? So this gives me a very, very non-trivial equation. The fact that the sum of conformal blocks in this channel, right, is equal to the sum of conformal blocks in the other channel. Okay? So these are what are called the conformal bootstrap equations. Right? And now these equations are extremely non-trivial. This is like an infinite set of equations. Because it's an equation that must be satisfied for any z and z bar. It's a complicated equation that involves infinitely many variables. So it's a functional equation for infinitely many variables. What are the variables? The c's and the deltas. Right? And now it's a challenge to solve these equations. Right? We can try to solve these equations. People cannot do it, but there's a lot that can be done. But really, attacking these equations and trying to use them to find good 3-point functions and deltas is something that right now it's something we are not yet mathematically capable of doing. Even though, I mean, you have in the blackboard all the ingredients. It's just a sum of hypergeometrics equal to another sum of hypergeometrics. And this you can think it's an infinite set of equations. So it's an infinite set of equations for an infinite set of variables, which are the c's and the deltas. And it's a very interesting question to understand how much can we extract out of it. Okay? But one thing we can do now is say, let me have another definition, definition 2, of a conformal field theory. Or let me write conformal theory. Okay? So we started with one definition, how correlation functions translate under dilatations. And now I'm giving you another definition. A conformal theory is a set of numbers, delta j, c, I, j, k, obeying the bootstrap equations. Okay. It doesn't look like the original definition, but the claim is that if you give me some set of numbers that give me some consistent bootstrap equations, there's nothing wrong with then saying, okay, so these are the correlation functions, 2-point functions, plug the numbers there, 3-point functions, plug the number there, 4-point functions, plug the c's here, and you can get now any n-point function and everything will be consistent. You can easily check that by doing 5 and 6 and 7-point functions you get no new constraints, so we already exhausted all the constraints we could get. And one second, and in this way, and we can thus, you could imagine taking this as a definition of the of a conformal field theory, which is a powerful definition, which requires no Lagrangian, nothing. It's just saying, if you have a conformal field theory, it's a set of numbers that obeys this constraint. Yes?
Do we always have an infinite number of primary fields?
Yes. The answer is yes.
Why is that?
It is easy to see that you need, because it's easy to see that these objects here have very different singularity structure. So for example, when I expand this object around z equal 1, this conformal block, this hypergeometrics, you might know that hypergeometrics at z equal to 1 have logarithmic singularities. Okay? But if I expand hypergeometric at argument 0, they are totally regular. So I have totally regular hypergeometric here, logarithmic singularity here. The only way it can work is if I have an infinite sum here that generates the logarithmic singularity. Other questions?
So, if you have like an Ising model, right, at the critical point, the CFT has then also an infinite amount of these primary fields properties? Or?
It does, yeah.
Yeah, so like these are, because like, so what kind of things do I have to think about if I'm thinking primary fields? Because I thought like, you know, magnetization maybe.
Okay, so since you insist, I'll now discuss the Ising model then. Okay. So let's think a bit. So I'll answer your question at length because I'll be discussing the Ising model now, but I want to know if there are any other questions. No. By the way, this is a okay. How do we know that if I give me these objects, right? If you give me this, that I get a good local field theory? That I have a good that it's a local field theory, something that's local, that I can discuss what happens at various points and so on. Okay. So the idea is, and let me try to explain what I mean by that. Okay, I'll tell. So, okay. So the idea is the following. This is a conformal theory. I did not say it's a conformal field theory. And if I want to add field to it, I don't want to keep the definition of just theory. I think it's also important. But it's a field theory. So if it's a set of numbers obeying bootstrap equations with one of the operators being a stress tensor, which has fixed dimension and spin. So if you have a stress tensor, if you can define a stress tensor, you have a local theory. But you might have theories where you cannot define a stress tensor, which would correspond to a non-local theory. Okay? Now, this might sound weird. What kind of theories am I considering? Is it something very pathological and weird? But let me tell you that there is very simple theories which fit into this that are conformal theories, but not conformal field theories in the strict sense. Okay? So here is a funny example of a conformal theory which is not a conformal field theory. Suppose I say that I have a theory where my 2-point function is equal to 1 over x minus y to the 2 delta. Okay, I'm postulating the 2-point function. And the higher point functions, are equal to weak contractions using this propagator. Okay? What would this mean? It means that this is equal to 1 over x1 minus x2 to the power 2 delta, 1 over x3 minus x4 to the power 2 delta. This will be the first term. And then if I factor out the first term, then I have 1 plus, and now this will be a ratio of this over the same thing, so it will be something like u to the delta, and the other one could be, I don't know, maybe uv to the delta. Okay, we would have to write it carefully and see what it is, but something of this sort, just to illustrate a little bit the point. So you see, this is a reasonable function. It's a function of u and v. It's a function of u and v that I could series expand and read off what flows and write an OP decomposition. It will be totally fine. It's invariant under permutations. For sure it will solve the bootstrap and so on. And nonetheless, if I do it, I don't find any operator of spin 2 and dimension dimension 4 to be my stress tensor. Okay? So this thing here is what is called the generalized free field. Because you see, it is just a propagator and a bunch of weak contractions, right? So if we would like to write an action for this field, what would we say? We would say this is an integral of phi, and then we want to put here some operator. So let me write what it is. So what is this? It's phi of x, some inverse of my propagator of x and y, phi of y, where I integrate over x and y. This definitely works. If I have x and y, it's just a quadratic theory. And if I choose this delta to be the inverse of the propagator, then definitely I get just weak contractions and things would be okay, right? But you see, this is not a local theory. It's not a local field theory. Now let me note that, so this is in 4 dimensions. If delta is equal to 2, then 1 over, or delta equal to 1, if delta is equal to 1, then this is just a propagator of a free scalar. Then this action becomes a usual one. Integral, one integral only of phi box phi. Okay? Which is the same as the integral d mu phi, d mu phi. Okay? Then it's a totally fine theory. It's a free scalar of mass 1, of dimension 1. It has dimension 1 in 4 dimensions, right? Because we have 1 plus 1 plus 1 plus 1 is 4. So it has dimension 1, delta is equal to 1, it's 1 over x squared, and it behaves nicely. But if I want to get something which has a funny power delta, I would have to use some kind of thing like this, which is not a local field theory. Okay? So this guy would have, of course, a stress tensor. So if I plug delta equal to 1 and do the expansion, I see a stress tensor. This one does not. Okay? But what is this theory, incidentally, by the way? What is this theory? How could you generate this theory in a funny local way? Can someone tell me? Of a clever way of translating this into some local description?
Integrate as an intermediary modal?
No, that's not what I had in mind. Another attempt? What would give this? So it's something that looks free, right? There are no interactions. It's just weak contractions. So you should be able to think only about the 2-point function. What gives this 2-point function? What would be a good time model for this 2-point function that we already saw, or you already saw in one of the tutorials or homeworks? It will be a particle in ADS. If I have a free particle in ADS, so if I have a free boson in ADS, d phi square plus m square phi square, but in ADS, okay, so this is in ADS, free massive particle in ADS, and then I postulate my correlation functions by saying, well, I just let particles evolve, but they are free, so they just evolve under all possible geodesics, which are not geodesic now. They are really, I could do honest propagators, or I could do geodesics. The conclusion would be the same. But I just sum over all possibilities, right? And each of them, because of the isometries of ADS, I'm guaranteed that each of them would give me just 1 over xi minus xj to some power of delta, which will be a function of the mass. And I'm guaranteed. So this theory that is not a local theory can be recast as a local theory, provided I'm willing to go to ADS. Okay? In ADS, it will be totally okay. Okay? So in fact, the moral of the story is that whenever you put something in ADS, that something that you put inherits the isometries of ADS. Right? You are putting something in ADS, ADS has some isometries, which means that there are some constant Hamiltonians that evolve things in some particular slices. And when I translate to the boundary, those generators become the generators of the conformal group. Right? So the idea is basically that if you have ADS, and here inside ADS you put anything, you put something. By something, I mean some massive quantum field theory. Okay? You put whatever you want inside ADS, a massive quantum field theory, right? The universe. You put whatever you want inside ADS. And then you study correlation functions of whatever I put inside as the points approach the boundary. This defines a correlation function x1 up to xn, which is a conformal theory. Okay? If the something, if we add gravity, if we add gravity inside also, then it would give a conformal field theory. With a stress tensor that you now have at the boundary being conjugated to the graviton that you have inside. Okay, so this was a small parenthesis. So now let's discuss, let's go on, and I'll come back to this parenthesis after discussing the Ising model. But I would like to tell you about some developments in studying the Ising model in 3 dimensions. So why, yes?
Can I ask a question about
Of course, yeah.
By adding gravity, do you mean you specifically when you can go into ADS, or it can be anything else as well?
Sorry, can you repeat the question?
So here we said that if you're willing to go to ADS, then you recover the conformal field theory. And you're saying that it's a conformal field theory if we add gravity.
If you put a theory of quantum gravity inside ADS, you get a conformal field theory at the boundary, because you are guaranteed to get the isometries of a conformal theory. But on top of that, because you have gravity, you have a stress tensor in the boundary. That's the claim. If you put a theory which is not a theory of quantum gravity, but you put your favorite quantum field theory, the Ising model, at a critical point, for example, inside ADS, you get a conformal theory, but it's not a conformal field theory typically, because there will be no one with the quantum numbers of the stress tensor in the bulk.
Some local field?
No, I don't think so. I think without stress tensor, I doubt it can be very local. Maybe it can be approximately local in some particular sense, but I think in general, it's a nice object also. But from the boundary point of view, it will not be local. Now, if you want to describe the physics, and if you allow yourself to go to the bulk, things are local in the bulk. So it means like points, they go inside the bulk, they talk to each other locally, and then they affect the boundary. So you do have a local description, like here in the free theory. Right? This theory, it's not local, definitely not local, but it's not crazy non-local. I mean, just by thinking in terms of ADS, suddenly it's already local, so it's almost local. Okay, very good. So I would like to tell you now about what people have been doing recently with these equations here, because these equations look very hard to use, but there is a way of trying to make use of them. Okay? So let's suppose I want to use these equations for studying the 3D Ising model. So what do I know about the 3D Ising model experimentally, or theoretically if you want? The 3D Ising model is a CFT. So it's a critical theory, right? So I have my magnets, and I tune the magnetization to 0. I tune the temperature to the Curie temperature. And then I have no scale, and I have a critical theory, right? So this is what I did as an experimentalist. What did I do? I had 2 knobs, temperature and magnetization. So it means, in the language of field theory, that the Ising model has two relevant operators. Right? Because there are two knobs that I need to tune to go to the critical point. Okay? So it has two relevant operators, which means two primaries of dimension delta smaller than 3, and then many irrelevant operators. Okay? Which means that this would be primaries of delta large. So these are operators that if I have my critical exponent and I can add interactions to it, that die off as I take large distances, but they are definitely there. So what are these two primaries again? They are related to changing temperature and magnetization. So these are nothing but sigma, which is called the magnetization, which is conjugate to the magnetic field, and epsilon, which is called the energy density, which will be conjugate to my temperature. Okay? By the way, let me remind you that the Ising model, which is a model of spins up and down interacting with nearest neighbors, is in the same universality class as the liquid gas phase transition. Because saying that I have spin up or down is the same as saying that I have 0 or 1, up to some trivial shift. And 0 or 1 means it's empty or occupied. So it's like a molecule, so is it dense or sparse or so on. And in that language, what you would call magnetization will be related to the pressure of the gas, and what you would call temperature would be related to the temperature. Okay? So because when we have a liquid-water phase transition, we know that all we have to do is tune the pressure and the temperature, or because when we have a magnetic system, we know we just tune the magnetic field and the temperature, we know we have two relevant operators. Okay, so what else do we know? We know that the dimensions are bigger than whatever unitarity tells me, which is called the unitarity bounds. Okay, which we derived some. For scalars, we derived that the dimensions must be bigger than d over 2 minus 2. Okay? And for general spin, there is similarly dimension for operators of spin L must be equal to the unitarity bounds for spin L, which is some known function. Okay? Okay, good. So this gives you an example, okay, of what we know. So it's not much. But it's not much, but it's something, and it's enough. Okay? So let me write then what do we expect. Okay? So if I say dimensions, and this would be spin. Okay? The unitarity bound tells me that the dimensions must be bigger than L plus D minus 2 for L bigger than 0, and delta must be bigger to D minus 2 over 2 for L equal to 0. So let's see, in D equal to 3, when I put L equals 0, I get 1, and here I get 1/2. So yeah, so if this is 0, the point is a bit below the point where I'm allowed. And I'm allowed to put operators here, and here, here, and so on. This is where I'm allowed to consider operators. Okay? And if here it's 3, I want to say that I have 2 operators in this range, and the rest are here. Okay, very good. So now the idea is the following. You make, so, okay, So now let me tell you how we can make this go forward. How we can make use of this. Now we can take the bootstrap equations and write the bootstrap equations in the following form. Sum over k, c 1 to k, c k 3 4, times some function, I'll use a different f, a straight f, k of z and z bar equal to 0. I just put everything on the same side and collect c times c. No, sorry. No, naively I cannot, no. Okay, so let me write more carefully. I can write it like this. C, O, okay, so C, sigma, sigma. So let sigma be the external operator that I'm considering. K square. And this is what I would do if I would consider 4 identical operators, for example, sigma, 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 sigma. Okay, the simplest experiment I can do, I measure the local magnetization and I consider 4-point function of 4 magnetizations. Okay? Any question? And this f is just a difference of 2. It's this f minus f, right? And now the idea is the following. So now there is the following thing that we have. The following observation is very important, is that this quantity, because of the square here, this quantity is positive. And this is a consequence of unitarity. Okay? And one way of thinking is that what we are doing here is considering the contribution of a given operator, right? And I can consider a symmetric configuration and use these arguments of reflection positivity to say that whenever I have something in the bottom and top, the contribution is something positive. Okay? So this is a positive constant. And here I have some functions of z and z bar. But I am adding up positive things times some functions f and getting 0. Okay? So the basic idea now will be to try to reach some contradictions and in this way rule out potential guesses for my spectrum. Okay? So here is how it works. So given a guess, so you give me a proposal for a spectrum delta, J, and this might mean, say, that we just say that the deltas are in this range. Okay? So a guess for these deltas could be, for example, saying that delta L bigger than D plus L minus 2. Is it minus 2? Yeah, minus 2. For L bigger than 0. And for example, suppose we say that delta of epsilon, okay, so delta sigma is equal to some, it's the external guide to some number, we fix some number, which could be, for example, 1.3. Then we say that delta epsilon, which is the first guy when you do OPE of sigma with sigma, you get epsilon plus other stuff. So this is the lightest guy, the one that contributes first in the OPE. Remember, the lightest ones contribute first. By the way, why doesn't sigma appear here? Parity, exactly, because sigma is magnetization, so it changes from sigma to minus sigma. So 2 sigmas are even, so epsilon is energy density is even. Similarly, in epsilon times epsilon, I will only get epsilon. But in epsilon times sigma, I will get sigma, but not epsilon. Okay? So epsilon, let it be, say, or let this guy be not 1.3, but say 0.7. And let's say this delta epsilon bigger than 1.6. And then we also say that delta epsilon prime would be the next guy that would appear, is bigger than 3. Because it's already irrelevant, an irrelevant operator. This is the kind of guess we do. So you see, basically the only interesting numbers are this one and this one. The dimension of the external guy and an hypothesis of where the epsilon could start. Okay, so this is our guess. We are going to make various guesses and change these two numbers. Okay, but we start with one guess. Now the rules of the game are the following. So first, we make a guess. Second step, we generate a functional, a linear functional alpha, which I define as follows. I define as saying that it is a sum of Cn derivatives with respect, or C, N, and M derivatives, N derivatives with respect to Z, M derivatives with respect to Z bar, of whatever it acts on, and after acting I put Z equals Z bar equal 1/2, for example, which is a symmetric point where U equal to V. Okay? So this is an example of a linear functional, right? But there are more functionals. Or alpha is a sum over some favorite positions Zi and Z bar J of whatever I have here evaluated at Z equals Zi, Z bar equals Z bar J, or a mixture of both, or any your favorite linear function, okay, with some coefficients, in this case Cij. Okay, so we generate some functionals that are parameterized by some constants C, by some constants, so some space of functionals. Okay, and now finally we say, and we generate, and now with the help of a computer we ask, does there exist a functional alpha such that for our guess, such that, given our guess, alpha acting on all these various differences of conformal blocks, okay, is, say, negative. Right? Okay? So now there are two options. The answer is yes, there exists. How do I know if it exists? Well, I construct one. It might be like taking two derivatives. Maybe it's enough for a given hypothesis. So if the answer is yes, it means that the spectrum that you proposed is ruled out, because you can never add up with positive coefficients something negative and get 0. But you might say no. Can you say no? No, you can never say, because it might be that you did not search well enough. So you say maybe. So it's either yes or maybe. And maybe just means that perhaps your guess is good. Okay? So this is a fun game that we can play now, where we can rule out spectra. Yes?
Why is this criterion with alpha and a criterion for us satisfying this, what we had in the top of the coin?
The idea is that, okay, maybe it was not obvious, but that's extremely important, because if it's a linear functional, if this is 0, this is 0. Right? I can act with alpha and it's a linear functional, it goes inside. So now what I'm saying is that if this is negative, we reach a contradiction. Right? So the idea is search. So we search for alphas, and the outcome is we rule out conformal field theories. We start ruling out conformal field theories. The subject of searching for alphas is one of the big subjects in computer science. It's called linear programming. And, and now we can tap into that knowledge and start looking for the optimal functionals. And whatever functional you find, I want to emphasize, even though it's something done with computers, once you find a functional, the bound you get is rigorous. You just proved it. It cannot exist. There are no error bars. So when you find a yes, it's a yes. Finita la commedia. Nothing you can do. It's done. If you find a maybe with a better computer, you might convert it into a yes later. But once you find a yes, it's a yes, and it's totally excluded. Right? So it's a method which is semi-analytic. It's analytic in the sense that the computer searches for functionals. Then the computer gives you a functional, and now it's analytic. You check analytically that it works, and there are no error bars. So this allows people, by studying this sigma-sigma correlator, to say, well, let me try to plot the dimension of sigma that I put in my guess versus the dimension of epsilon minimum, which means that this value that I put here, say that it's at least this value, it might be bigger, and see what's allowed and what's forbidden. And what people found was a nice plot that looks like this, where this is a maybe, and this is definitely excluded. Meaning that, let me give you some numbers. Meaning, for example, that if this point is, say, 0.6, like in the example I said, and this is like 2, the claim is that there is no conformal field theory with where you have a relevant an operator of dimension 0.6, and then the next operator is heavier than 2. No, it cannot be. If it's dimension 6, the next guy must be below some point here. It must be here, somewhere here. Okay? So you prove right away that if sigma is this, epsilon cannot be so big. Epsilon can be maybe 1.5 or something like that. Okay? And then people also observed that in this plot there was some nice kink that was actually quite sharp. And then this kink, actually here in this kink is at 0.518, and here 1.41 something. And people knew experimentally that this was exactly the values of the critical exponents of the Ising model. These are indeed the values of delta epsilon and delta sigma of the Ising model. But, well, right now we did not fix it. We just said this is allowed, this is excluded. It looks like a coincidence that at the kink there's something. But last year, or maybe 2 years ago now, it was, when was this? I think it was maybe 2 years ago. Yeah, 2 years ago. Simon Duffins and collaborators went on and studied not only sigma sigma, but also epsilon epsilon, sigma epsilon, and expanded the search and asked what happens now when I also impose sigma epsilon and so on. And when they did it, the plot became much more amazing, and it became such that there was an island. Instead of all this region, it became an island, and this is when we use multiple correlators. So we use sigma and also we use epsilon, not just sigma. And suddenly, we say that if you have only 2 relevant operators, which is an experimental fact of daily life, right? Your quantum field, your conformal field theory must be inside this island. Okay? So here is the island. I can show you. So here is the plot. The island is the point that you cannot even see. You have to zoom in several times to see what the island is. And in fact, the island, the size of the island is smaller than the best error bars by any other method. So it's actually the best determination of the critical exponents of water-liquid phase transition right now. It's using this method, which is quite amazing that with so little information, all we said is, well, I have temperature and magnetic field, and that's it. That's the only thing I have to tune. And it's a conformal field theory. And we got the best values possible for these critical exponents, which have like 10 digits now or something like that, something crazy. It's really, really super, super tiny now. Okay, so this is a nice development of this story. Let me point out any question here. Let me take questions maybe now. This is very unusual. So if you are, I bet you never saw anything like this before. It's a very different. I think it's simple, but it's very unusual, this kind of arguments. And it's not something we are typically used to, this step. Make a guess, look for functionals. It's not the typical start of a physics argument, but it's a powerful one.
Representing magnetization in energy density with primary operators instead of, let's say, secondary operators, is that by choice or do you have to?
No, they are scalars, so they better be primaries. They are not derivative of something, right? We know that. And if they were descendants, it would mean that there is someone which energy is even lower. So then it would violate the hypothesis of having just two relevant operators. We know we have two relevant operators that are scalars, right? It's not like we have some, right? So if they were descendants, they could be, because it could be like I had with derivatives contracted. But I would need at least two, so it means that I would need at least 6 operators of dimension smaller than 3, right? The 2 guys, and then I would have to, I would still have need primaries nonetheless. Okay, any question here? Yes.
So in general, like, suppose you want to study a model, but how do you know what kind of operators that exist in this model? Like, for example, here we assume that there exists like a sigma epsilon.
Yeah, I mean, this is it's an experimental fact. I think you need experiments. Physics is about experiments. We should respect them. It's very important. But in general, you could now that we know that such islands exist, we could just blindly scan for all solutions of these equations and look for various islands, and the various islands would be the various possible theories that exist in nature. It's just that it's hard. If you have a guess about the spectrum, it helps you a lot. Zoom in and analyze a smaller region. Okay? So this was really something totally, I think, it's totally remarkable that this works. These equations were proposed by Polyakov and others in the beginning of time, and they were dormant for the longest time until in 2008, when Ryzhkov, Ratazi, and friends started asking these other questions of saying, let's not try to solve them to be so ambitious, let's not just use bounds. Let's just separate what's possible and what's not possible. And actually, when they started, their motivations was in phenomenology, to show if some relevant operators could exist, that would explain the Higgs as some kind of technicolor and so on. So it was very different prescriptions. They wanted exactly to see, could I have some operators of a given dimension? And they did manage to do what they wanted to do. And it was a big surprise that this idea of going to bounds, this is the kind of thing you would expect. And the fact that we are starting to have islands which are really, really super, super small is very encouraging. And it became not a method for just establishing bounds, but a method for precision determination of critical exponents. And it's really a beautiful topic, I find. But now I would like to point out something fun that which is that here we used this kind of ideas to learn about a complicated critical theory. By the way, why did I choose 3 dimensions and not 2 dimensions? Because 2 dimensions is exactly solvable. It's one of the minimal models. This method also works, and it reproduces the known results, that sigma is 1/8 and epsilon is 1. It's fine, okay, it's good that the method works. But what's fascinating about this is that the 3D Ising model is a strongly coupled interacting critical exponent where you don't have perturbative tools or anything else to start computing. Okay? Now, given this idea that I can actually not only study critical exponents, but I can do other stuff. I can take a massive quantum field theory, put it inside ADS, even if it's a massive quantum field theory, and get a 4-point correlation function that will have that form there as a sum over conformal blocks. This will still be true, even if my theory is massive. Even if the theory that I put inside is massive, that I will get a theory at the boundary which is a conformal theory. So there is something which is not a duality, because it doesn't go in both directions, but there is something that you put some massive quantum field theory in ADS, and this gives you, in one direction, a conformal theory. It defines for you a conformal theory at the boundary. Okay? But we now see that we have powerful tools for constraining the space of conformal theories. So the question is, can we use conformal bootstrap techniques, conformal bootstrap, to learn about massive quantum field theories? Huh? Because, okay. So how would the dictionary go in this case? So we saw already in your tutorial, in your exercise that you did, that if you have some dimension delta J, this is equal to the mass mj. If I put some particles in ADS, the dimension that I get is related to the mass. In fact, if I want to be totally rigorous, you see there's something fishy. M as dimensions, delta is a number. Right? So why? What's going on? Well, the reason is that we always work in units where the ADS radius is 1. But if I put the ADS radius, now it's good. Okay? So this is just the ADS radius. So if I put, which typically we set to 1. And imagine I want to put something in the middle of ADS. So I want to have ADS. And I want to put something here in the middle that fills approximately flat space. In other words, I want to consider the radius to be large, or in more physical terms, I want to say that the radius is much bigger than the wavelength of my particles, which is the same as saying that my particles don't fill the box, so they are much heavier than 1 over the radius. Okay? It's just absolutely equivalent. So in this regime, right, I'll be putting things in a huge box, and in the middle of the box I will have approximately flat space. So in this limit, when this guy is much bigger than 1, I am in this regime where I see approximately flat space in the middle. But if I want to extract flat space, notice, I don't want to ask what is delta, because I don't care about R. R is an artifice. I just put R to put things in a box. Well, but that's fine. So the dictionary goes that I should take delta I over delta K, and R cancels out, and I get mj over mk. Okay? So the first entry of my dictionary is that what I should do is take a conformal theory where these deltas are large. So the limit, when all deltas scale to infinity with the ratio fixed, is given by the ratio of the masses of whatever quantum field theory I put inside ADS. Right? So this is the first entry of our dictionary. It relates dimensions in a conformal theory to masses in a massive field theory. Okay? Good. Yes? I want to take delta to infinity because I want to reproduce flat space physics. I want to learn about quantum field theories in flat space. Okay? This is important. I mean, my goal is to learn about, say, glue balls in QCD. Or what happens to the Ising model when I go away from the critical temperature and I flow to a massive quantum field theory, which is an interactive massive quantum field theory. And now I want to ask what happens to the Ising model as I flow to an interactive quantum field theory by turning on the magnetization, for example. Right? But I want to know in flat space. I mean, I don't care about liquid-water phase transition in some hyperboloid. Right? I want something useful for my experimentalist friends. So we want flat space, so we take the deltas to be very large. What about a cubic coupling, G, I, J, K? Okay? Imagine I want to measure a cubic coupling. What should I do? Well, I consider a 3-point function. And a 3-point function, like you were drawing in your exercise, of 3 points that meet and they interact. But will I write an equation like this, like C, I, J, K, when the limit, when all deltas go to infinity, is equal to G, I, J, K? Of course not. I even left some space to correct it. Right? Why? Because remember from your exercise, you had your points and you had 3 points, and you studied that these minimal geodesics that go from here, here, here. Right? And what did you put when they meet? You put nothing, because I told you, I did not tell you to put anything. But if there was a probability of this particle splitting, you would compute this and then multiply this by the coupling, G, I, J, K. This part here, which describes the propagation inside, should be amputated. It's not part of the interaction. The interaction is just what happens here. It is just the G. Right? So the recipe is take these C's and divide out by the propagation part, which you computed in your exercise. Okay? With interaction 1. And take the limit. And it goes. And if you did the exercise that I told you of seeing how this behaves when the deltas are large, you will have noticed that this is exponentially small in the deltas, which makes sense because of these geodesics being exponential. It takes some length of the geodesics to go there, and therefore there's some exponential suppression because it's our classical particles propagating, and this is exponentially small. So these 3-point functions will be exponentially small. So we will have to. Whatever we will do, and we will do numerics like here, we'll have to have lots of precision because we are looking at an exponentially small quantity, dividing by an exponentially small number, and getting a number of order 1. Okay? So, but this is then how the dictionary goes. Okay. But now I can start asking the following kind of questions. I can say, for example, suppose given some spectrum Mij, Mi, given some spectrum of masses, for example, I could go to the Ising model, turn on magnetic field, and measure the masses of particles. For example, in 2 dimensions, there are 3 particles, and I could measure their masses, and their mass is like 1, 1.4, 1.6. So given some mass spectrum of a strongly coupled field theory, so given some mass spectrum of some strongly coupled quantum field theory, and it doesn't need to be strongly coupled, but it's much more exciting if it's strongly coupled because I cannot compute otherwise. So given the spectrum of some strongly coupled quantum field theory, I can ask now the question, what is the maximum value of the coupling, say, between M1, M1, and M1, assuming a cubic coupling exists? Why should such questions make sense? Because the intuition is that if I have some scalar particles, say, interacting by exchanging of another scalar, if the interaction strength becomes bigger, the attraction between them becomes smaller, and therefore the bound states that they form, the other particles that they form, should become lighter. So given some spectrum, right, if I increase the interaction energy, if I increase the binding energy, it will lower the energy of the states. So I postulate some spectrum, M1, M2, M3. I should be able now to say G can only be this big. If G was bigger, the spectrum had to come down by quantum effects. It should not be possible to have this. So that's the intuition why such thing could exist. Now, can we now solve this problem? Well, now this problem translates into the problem given some deltas, what's the maximum C that I can have of C, say, sigma, sigma, epsilon, the analog of, right? Imagine epsilon was the first guy that appears in that model. It would be, what's the maximum of this coupling, say? And then I translate back using this dictionary. So now, this problem here, it's not exactly the problem that I told you before, but it's also a problem that you can also think from this functional point of view. So if you are interested, I can tell you how exactly I would formulate this. So now we are not ruling out spectrum, we are ruling out 3-point functions. I'm saying that the 3-point function can only be this big. If it was bigger, there would be a problem. And you can easily figure out what's the idea. So right now, we say positive stuff times something is positive stuff times negative stuff is impossible. Now, if we want to put a bound on C, we will keep one of the terms on one side, the one we want to put a bound, and everyone else we will put on the other side. And then we would say, well, if I can act with a functional and make everyone on the other side negative, then I have a bound on this one here, because I know this one is at least, say, the first one there, and the other ones are all positive. Right? Maybe this was probably a bit too fast. Do you want me to explain how to get this? It's not complicated, but yes? I'll tell the rest. Okay. So we could write the previous equation as saying that I have a C square sigma epsilon times the exchange of epsilon equal to minus C square sigma identity minus sum over K of C square sigma and the other operators OK. Okay? Notice that when I exchange the identity, I just have the disconnected contribution, which has conformal block equal to 1. Okay? Because basically if I exchange the identity, you see, there's nothing flowing between 1 and 2, and I already have the disconnected part stripped out. So this is the equation I get. So this is equivalent to what we said before. Now suppose I act with a functional on this equation. Right? And I act, sorry, here I forgot fk. I act with a functional here, and I get alpha acting here, alpha acting on 1, and alpha acting here. And now suppose I find such spectrum where this thing is negative. Right? If so, this stuff here is bigger or equal than 0. And therefore, this thing here is bigger or equal than minus C square sigma identity, which is actually 1 because it's just a 2-point function, times alpha of 1 over alpha of f of epsilon. So I put a bound on this structure constant. Okay? So it's about looking for functionals which make this negative for everyone but don't care about the identity, and this gives me a way of bounding this. Okay, well, if you don't mind, let me just finish this short thing. So now we can ask this question, and indeed, we can run numerics. We can run numerics and find that we can indeed solve this numerics. And for example, as an example, we can say, suppose we consider the following spectrum. So here is 0. Here is delta external, which would be the analog of dimension of sigma. Okay? What do we do for this guy? We put some big number, like 100 or 200. Now we are doing big, right? Remember, these deltas, we want them to be big. Then here we put some delta of the exchanged particle, which would be the analog of delta epsilon. And the ratio of the two, if I call this M1, and this would be M2, the ratio over 2 I keep fixed, but I put these two guys to be big. And then here I have 2 delta external and a continuum, because there are many, of course, many operators corresponding to 2 particles. The 2 particles can be quiet, or spinning a little bit, or spinning more. So there is a continuum, the usual 2-particle continuum. So we make this hypothesis now, our guess for our spectrum to be this. Right? With this ratio fixed, so M2 over M1 fixed. And we ask, what's the maximum of the coupling G between M1, and M2 as a function of the ratio M2 over M1, that of course goes from 0 to 2, Because when M2 is twice M1, we get into the two-particle continuum. Then it's no longer a particle. It becomes a resonance. And this is a plot done in 2 dimensions for 2-dimensional quantum field theories, which corresponds to, in the boundary, to 1-dimensional conformal theories, which is kind of fun. It's a very simple conformal theory. It just lives on a line. We can now use this and say that there is indeed a maximum coupling, and these are allowed quantum field theories, and these here are forbidden quantum field theories. Okay? So it's an example of an application, not of ADS-CFT, but of ADS-CFT related ideas for studying massive quantum field theories using the power of the bootstrap. And the conjecture would be that the physics of massive quantum field theories in d plus 1 dimensions, the bootstrap of S matrix of massive quantum field theories in d plus 1 dimensions, is contained in the bootstrap of d dimensions, of one less dimension. So it's kind of, if you think about it, it's kind of striking. I'm saying that if you study conformal field theories, which are simpler than massive field theories, you are learning about massive field theories in one more dimension. I personally find it very, very striking. Yes? Sorry for taking so long.
The masses of Q of t, you have to tell me at which scale you're looking at, right?
No, by masses I mean, how do I define a mass? I define a mass by saying my correlator, when I take the points very, very, very separated, decays as e to the minus mass times r. That's my definition of the mass.
Okay.
Right?
So it's at 0 energy, loosely speaking, if you do it like
it's at very large distances, how things decay. Or said differently, it's really the mass of particles when they scatter. Right? If I have glue balls, right, you don't ask what's the mass of the glue balls at different energy. You just say, if I am in space like an astronaut and there is a glue ball, it has some mass, right? Am I right? Do you agree? Then if I zoom in and I start studying correlation function at high energy, the description of this freely moving glue ball is no longer applicable. So then I start seeing that the 2-point function of 2 glue balls is at very short distances a power law, at very long distances an exponential, and in the middle something complicated. And that something complicated, you can there put some parameter that you call mass that depends on the scale. But I would say that in that case, what I would call mass is the mass of things when they are at low energy, at 0 energy, and when they are just moving freely. So that's the definition we want to take. It's the S matrix definition of masses.
So in that plot, what's in the middle of the region that is allowed? Is it infinity or just 1?
Yeah, it's infinity. Yeah.
Why is it infinity?
I can tell you, but it takes more time. It takes more time. It's not very important. You see, there's no contradiction being infinity. It just means if the plot is infinite, it means I cannot do bounds. Me not being able to do bounds, it just reflects that I'm not smart enough. It doesn't tell anything about nature.
And another question.
What's interesting is that sometimes it's not infinite. So sometimes we can rule out things. Yes?
It's about the coupling constant. So the GMM is running with our scale, like in the massive theory. So does that mean like we need to consider the scale in this picture or not necessarily?
I'm not sure I understood your question. Are you worried that G has dimensions?
Yeah, it's not.
No, that's true. Yeah, I'm measuring here G. Yeah, so let me put G hat. G hat is G divided by M1 squared. G has dimensions of mass, so let me use my lightest mass as my kilogram or my pound.
Yeah, I mean,
then,
G is also running with M, right? So our scale, energy scale changes, G will also.
Okay, so the definition of G that corresponds to this kind of plot would be if I scatter, again, my particles, which can be my glue balls or my excitations of the 3D Ising model, and I consider the S matrix, then this process will have a G square divided by the energy at the center of mass minus the mass of my particle, and here there will be 1, 1, 2, which would correspond to this process here, right? And this is the definition I'm using, where this G is again, some infrared quantity, which appears square because there are two couplings here and here.
G is for random, not an arbitrary scale.
Yeah, that's true. But it's okay. Yeah, that's true. Okay. Anyway, this was just a small detour, and so this tells you a little bit about. So we start now going back to ADS, and in the first half an hour of this afternoon, I will go even more into ADS, into more standard ADS CFT things, and tell you a little bit. So now if we go back to ADS, how do we start applying these kind of ideas of computing the CFT data and exploring the CFT data for n equals 4 super Young mills? And what do we learn about ADS CFT when we start doing that? Okay? And now we start closing the gap and coming back to the beginning. So this is already partially doing that. I should mention that this stuff is work with it's work in progress with Panadonas and John Toledo, who is a student here, Balt van Ries, and Miguel Paulus. So it's going to appear in a few weeks. This is 1 year old by Simon Duffins, that stuff. So I should have given more references. Thank you.